Welcome to Physics Made Easy channel. Today's topic is reverse biasing, and we will draw its characteristic curve for reverse biasing. Before that, I will revise you the basics of reverse biasing. Now, this is reverse biasing. What happens in reverse biasing? Positive terminal of battery is attached with N side and negative terminal of battery is attached with P side. This is the positive terminal of battery. This is attached with N type or N side of the PN junction, and this is the negative and it is attached with P side of the PN junction. Now important point is reverse bias increases the width of the depletion layer, and it also increases the this barrier voltage or barrier potential. And this current in reverse bias is due to minority charge carriers known as reverse current, and it is in micro ammeter, that is 10 raised to power minus 6 amperes. And barrier increases, we have already discussed. Minority charge carriers are the main charge carriers. Resistance increases and width of the depletion region also increases. Reverse current or leakage current is due to the minority charge carriers. And now let us come to its reverse biasing characteristics. Reverse biasing characteristics means the graph between V and I when we put the PN junction in reverse bias position and we increase or decrease the voltage, then what is the effect on current from the junction bias? So that's we are going to study. Now current during reverse bias is called reverse saturation current. Its values are the order of few microamperes. I have already told you this thing. It is due to drift of minority charge carriers, and it remains constant up to the Zener breakdown voltage. Now what is the Zener breakdown voltage? It is the peak inverse voltage. Note this line. This is the peak inverse voltage of the diode, is that voltage at which breakdown of the junction diode takes place and current increases to large value and resistance decreases. When the reverse voltage across the PN junction is increased to breakdown, the reverse current suddenly increases to a large value. The breakdown voltage varies from 1 to 2 volt to several hundred volts. Now, this Zener breakdown voltage VZ, Zener breakdown voltage VZ. Now its range is from, you can say, 1 volt to uh, several hundred volts, means maybe roughly I can say 500 volts. So this is from 1 volt to several hundred volts, not 500. I have just assumed 500 to make this mathematical equation clear. And now VZ is dependent upon dopant density. DD means dopant density or impurity density. So this reverse uh, breakdown voltage, peak inverse voltage or Zener breakdown voltage varies from a few volts to a few hundred volts, or its value depends upon the density of the dopant atom. And next, this is the graph. For example, reverse bias current, note down its unit is microampere. Reverse breakdown current is in microampere. This is the reverse conduction, and here breakdown takes place. At breakdown, note one thing: this voltage is constant. Then onwards, it remains constant. And this current increases to a large extent. I increases, it means resistance will decrease. Obviously resistance decreases and I increases. So in fact upward arrow denotes increases, so I will change these letters. So I will just write I increases and resistance, which stands for R, it decreases. Now, for drawing these characteristics, again we have got p-n junction. This is a p-type semiconductor represented by a filled triangle, and this is n-type. And microammeter is used to measure the current, and V is used to measure the voltage, and this is the battery, and this is rheostat which varies voltage. This rheostat varies voltage. Now for reverse biasing, V is negative. Now for reverse biasing, V is negative, and this is E is equal to E raised to power. Normally the expression for I is I naught into E raised to power EV divided by KT minus 1. Now here V is negative. Because V is negative, it means this is very small. So we reject this factor. So in this case, reverse current IR represented by IR, reverse current is approximately equal to minus I naught, or some basic value of the current minus I naught. Now how do we calculate dynamic resistance? Dynamic resistance, it is the ratio of small change in applied voltage to the corresponding change in current. So this is roughly delta V. R dynamic resistance R is delta V by delta I. Forward bias is small, and now we will see the portion of the curve. Here, this is the curve in forward biasing. So we are trying to calculate its value in forward biasing. Now this topic is very important. Questions have been asked on this question in your board examination, in your NEET examination, or even in JEE Main. This part is extremely important, kindly, and very easy as well. And I will also tell you the pitfall. Now, delta I. Suppose someone has asked us to calculate the resistance at some particular point A. We will have some small interval around A, for example E and C. We will see the difference between the voltages at E and C represented by delta V, and the corresponding difference in the current represented along y-axis, and then delta V divided by delta I will give us the value. Now, what kind of error we can come across? For example, this is in milliampere. Remember this thing. Current here is in milliampere, and here is the voltage. And now what error normally students commit? They ignore this 10 raised to power minus 3 factor. So this 10 raised to power minus 3 factor in current is basically the pitfall. We will just suppose, hypothetically suppose this difference is 6 ampere, 6, and here suppose it is 3. I'm saying hypothetically. So we will just divide 6 by 3 and say that the resistance is 2. This is not the case. Or sorry, 3 by 6 delta V by delta R, this is 1 by half. We will say 0.1 by half ohm is the resistance. No, not at all, because this is in volts and this is in 10 raised to power minus 3 in amperes. From here we will calculate the resistance. Now resistance in reverse biasing is very high. Now let us assume this problem. Resistance in reverse biasing is very high, RD. Reverse biasing resistance RD delta V by delta I. This is ST, for example, ST by UR. See from here. So this is This portion corresponds to delta V. This portion, particularly this, is delta V. I will exactly draw the diagram. Delta V. And this portion is delta I. This is delta I. Now, if I try to calculate RD roughly now, suppose I try to calculate RD and I want to find its rough value. Now the rough value of RD, uh, RD equal to delta V. Delta V, I can take it as minus 4. I will just ignore the minus sign. Basically, this is minus 4. Now another fault. Minus, you will forget the symbol with this. Minus 4. With minus 2, the current is this. Now, if I take a rough idea, this is 1 micro, 2, I take this as 3, 1, 2, 3, 4. You can roughly take it as 1 micro. So the final current is 5 microamperes and the remaining is I have taken it as 4. I have taken it at 4 microamperes. So here microamperes, we will actually forget this symbol of micro. Now see here, minus 4 plus 2 divided by, this is 1 into 10 raised to power minus 6. So resistance here comes out to be minus 2 into 10 raised to power 6. Very huge resistance. Very huge resistance. Very large value of resistance. And in the very next portion, above the threshold voltage, the diode characteristic is linear. In the linear region, ID is almost independent of V and Ohm's law is obeyed. And now, applications, two very important applications of diode. One is they act as clipping circuit. If we have to clip a part of the wave, for example, this is the wave and we want to clip a part of the wave. We don't want wave above this level. It means we will use diode circuit to clip the wave. Now we shall be having wave only of this order like this. And next is clamping circuit. Suppose we want to shift this zero line. We want to shift this zero line from this level up to this level. Then what we will do? We will use the clamping circuit. This is the clamping circuit. This is the clipping circuit. In clipping circuit, we apply the input here. Here is the resistance. This is the diode position. And we take output here. In clamping circuit, now we have used a capacitor here. Instead of resistance here, we have got a capacitor. Then diode in parallel with the load resistance. We take the output across the load resistance. And note it down here. This is the zero line. Zero line is in between VM line and minus VM line. And now zero line has shifted to the bottom. And this is VM line and this is 2 VM line. So this is how we have shifted it. Now another application of this is, and that application is of rectifiers. Rectifiers. So they are used as rectifier. Rectifiers, this is the case of a rectifier. We will do it in the next lecture, but I will just show you the diagram. So this is the input. We convert AC, this is AC signal, and we convert it into DC like this. And after improvements, we may get in, that was a half wave rectifier. This is a full wave rectifier. In full wave rectifier, we get curve like this. And the general AC component is further decreased if we make use of these filter circuits. Now if we make use of filter circuit, now this AC component has been reduced greatly. And there are further applications, you can further improve it. What is important to learn is that rectifier, they change AC signal into DC signal. So there are three very important applications of diode. One is clipping circuit, second is clamping circuit, third is they are used as rectifier for rectification purposes. In reverse, we have just done reverse bias characteristics. Reverse biasing characteristics, we know that the reverse saturation current is of, if it is of the order of microamperes, that is 10 raised to power minus 6 amperes. Minority charges, they contribute to the flow of the current, and there is a peak inverse voltage. Peak inverse voltage is the voltage at which the junction diode breaks down, and peak inverse voltage can vary from a few volts to few hundred volts. The value of the peak inverse voltage depends upon the density of the impurity or the dopant atom. And this is the curve of reverse biasing, and this part is known as reverse conduction part, and this part is known as breakdown part. Note that the voltage is constant at breakdown. So this very characteristic of diode is used for stabilizing the or for regulating the voltage. And this is the basic circuit, and from the graphs we calculate dynamic resistance. For example, this is the graph. We have studied how do we calculate dynamic resistance by making use of RD is equal to delta V by delta C. Here it is EC by FD. This is EC, EC is this gap, and FD is this gap. Here we have taken a simple numerical example, and then we applied the same to reverse bias position. We note that resistance in reverse bias is very large, and here resistance is of the order of, if I fill this, if of the order of 500 ohm or 600 ohm, and resistance here is of the order of 10 raised to power 6 ohms. So reverse bias resistance is very large, and then we did application. With these words, before finishing this lecture, I will request all of you to, if you like the video, then kindly like it, share it, or comment on it, and or subscribe it. And if you don't like, then kindly write it back so that we can improve ourselves and serve you in a better way. Thank you very much.